A given P. Your book actually says 2A given P. I found that a little less understandable, so I changed it to find A given P. But he's saying convert to A given P is what he's trying for there. Alright, in our case, we will use the formula listed in the book, or we will use the factor listed in the book. In our case, it's obviously quite a bit easier to use the factor if it's possible. For instance, if the interest rate was 6.3%, then I'd use this equation because it's easy. Just put in 6.3% and crank it out. And the tables do not have a 6.3% value. We're asked to deposit $1,116.47. That is the present value that we're going to put in. The amount we would like to extract at the end of the next year and at the end of succeeding years for 7 years is can be found by multiplying the present value times A over P. P cancels P, appears to, leaving you A. That's what I want to know. How much can I withdraw? If you go in and you use the A over P column on the 6% page on the 7-year row, you'll find it's 0.1791. And so it also comes out pretty close to $200, $199.96. That's the same thing we found on the previous problem. So what it kind of sounds like is that if this, where you put in 1116.47 and can take out 199.96 is the same as being able to put in 199.96 and take out $1,678.76, then we really probably ought to find that this is the same as this, equivalence, value-wise. Let's see if that turns out to be right. What we're saying is that an annual investment of this for 7 years at 6% has an equivalent present value of this and an equivalent future value of this. Looks like P ought to be the same as F. In other words, it looks like that if you were to solve for this future number, F, knowing a present number of 1116.47, you ought to get 1678.76. So we take 1116.47. We want to change the present value into a future value, which we think we know what that future value is, but we're checking it. Use the 6% table, because there's more than one on a page here. Use 6% table. Use the 7-year row. And the factor is 1.5036, which does indeed give us $1,678 and about the same pennies. Pretty close. Alright, now then, let's assume that you would like to find F knowing the annuity. A minute ago we took F and found the annuity. Then we took the present value and found the annuity. Now I'm saying, let's say that you were able to extract from your yearly salary some amount of money and put it in the bank at the end of each of these years. After 7 years, how much money would you have? Including the fact, of course, that you have this one in your pocket. You may not actually put it in the bank, But when you walk out of the bank, you'll have the one you gathered for this year, and what he gives you, what total future value will you have. The formula for that use is A onto 1 plus I to the n minus 1, or in economics notation, we would say A times F over A. So what if we want to invest $199.96 for 7 years at 6%? How much will we be able to collect at the end of 7 years? Well, we know what the answer ought to be, because we just turned around and turned this number into an annuity, and we found it was $199.96. So what we ought to get is the same number we stuck in here a minute ago. We do that by multiplying $199.96. We use the F over A column, the 6% table. That's correct this time. 7-year row. The factor is 8.3938 if you'll check that in the book, which gives you $1,678, which is almost the same as we got before. There's only 4 decimals of accuracy on the number there, so you're not going to get exactly, but they're also not going to ask you answers that close either. How would you find the present value of a future annuity? Well, you turn the original equation we had around. In this case, if you wanted to put $199.96 in the bank for 7 years, how much would you have to put in now? You can solve that the same way. Present value is equal to, you're given the annuity, you're given the annual amount, you want to find the annuity, this is what you're given, you multiply what you're given times P over A, such that A appears to cancel A, leaving you P, which is what you want. So you use the P over A column on the 6% table on the 7-year row. Comes out $199.96 times the factor you'll find in the book, 5.5824, and that says that this amount here is how much the present value would be. Now, a lot of times you have cash flows that are not constant per year, or constant per month, or constant per payment period. In that case, they are called, if they are linearly increasing, they're called a gradient. And again, you and I will have to agree on some common year as to when to start putting the gradient in. Otherwise, we're going to have a whole pot full of different tables. One table might say, let's assume we put the first non-zero gradient number right now. Another table might be, let's say, since a gradient is a straight line going through 0, let's put 0 right now, but put the gradient, first non-zero gradient, next, and so on. You could end up with half a dozen tables. Well, if you and I had done it, we might have done it differently. It's too late for that. It's been decided. And it has been decided that if the present value goes in now, right now, then the gradient starts at year 1, and we include the don't deposit any money now. And let me just jump ahead a little bit to show you why that works out nicely. The reason is many times you will have present value now, and you want to take out money like on an A constant rate, annual constant rate, and on top of that you want a gradient. Well, if you put the first non-zero gradient back here at the first position, then you get A plus G here. It's a little confusing. So what they've decided is, because you often work problems like this, put the money on time 0 if it's a present value you're willing to invest today. Then how much you can take out of the bank if you want to take it out in gradient fashion. Put the annuity starting on time year 1, and put the first non-zero gradient number at the end of year 2. So that says that for us, we have a gradient, which will now have to follow the rules. You'll find many times the problems don't follow the rules to see if you really understand the rules. But if you want to take money out in gradient fashion, the rules are the first non-zero number goes at the end of year 2. The gradient begins at year 1, as does an annuity begins at year 1. Note also that you don't have to use these equations. You can use the P over G column if you're given the gradient to get P in a high percent table in year row. Now then, also I believe that